We're going to look at some extra products, and in this case, we're going to look at the term insurance. We're going to start with the continuous time product. So what we're going to do here is we're going to look at an insurance product that pays at the moment of death, but now only if my policyholder dies within a fixed term of n years. So the difference with the whole life insurance is that now the duration of the contract is limited. It's limited to a period of n years. So how do we represent the present value random variable z? If the benefit is €1, then z will take or can be expressed as v to the power tx if the tx is less than or equal to n, because there is the duration and the limit in duration of this particular contract. If the tx is beyond n, then the insurance will not pay any benefits. So the present value random variable will then take the value of 0, right? So the difference here is just the limitation in the duration of the contract. Tx cannot just take any positive value. Tx should be less than or equal to n if the insurance benefit of €1 is to be paid at the moment of death. So if we look at the actuarial notation for this product, now things get a little bit complicated. So we recognize the capital A because we're dealing with an insurance product. We recognize the bar because we're working in continuous time. We recognize the X because we sell this product to an X-year-old. But now we also have the duration N with an actuarial angle, and that's this, the bracket that you see over here with the actuarial angle around this N. And moreover, we've got a symbol here, the 1, which is a superscript and which denotes the particular fact that this notation is used for a term insurance. And the 1 is put on top of the X because it refers to the fact that this insurance product is going to pay if the death of X happens first, happens before the end of the duration of n years. So that also means that later on today, we will see examples where we put the superscript 1 on top of the n. And that's then a different product that we refer to. But if the 1 is put on top of the X, the age of the policyholder, then it means this product is going to pay a benefit if X dies before reaching the end of the duration, the end of the insurance cover period. Okay, so that's what we refer to. We're going to work in continuous time, right? So that means we're going to work with an integral notation. We're looking at e to the power minus delta t, which is my discount factor. And then I've got tpx multiplied with the hazard rate function for hx plus t. So tpx multiplied with mu x plus t. Remember that these two guys together, that they give us the expression for the density, the probability density function of the tx random variable evaluated in t, right? So this is what we derived last week, or what we explained last week, using the expression for the expected value of a transformation of a random variable, right? The only thing that is changing in my integral notation for this particular product is now that I do not take the integral until plus infinity or until omega minus x, but I take the integral up to duration n, right? Because the €1 benefit is only payable if death occurs within this time period of n years since the moment that my policyholder reached age X, right? So that's important. We limit the duration of the contract. If you continue the same reasoning, if you look at the second moment, you'll get a completely similar expression as what we obtained earlier on. Once again, the duration, the upper bound of the integral is now equal to n because of the limit in the duration of my contract. Okay. I'm going to do the same thing now, but not for the continuous setting, but I'm going to switch to the annual setting. So still we're looking at a term insurance product. So the period during which my benefit is payable is limited. It's limited to duration of n years. And in this case, I'm looking at an annual contract. So that means I'm working in discrete time. My product is going to pay this benefit of €1 at the end of the year of death, right? So thinking about what we did last week, once again, we have the present value random variable z for the benefit of €1. And that's here going to be, or the z, we're going to express the z as v to the power kx plus 1. If the kx is less than or equal to n minus 1, right? So the ultimate value that the current future lifetime random variable kx can take in a term insurance contract with a duration of n years, the ultimate value that kx can take is n minus 1, right? Because that means that you're gonna die between time n minus 1 and time n, right? You cannot go beyond time n because then the duration of the contract is expired. If kx takes a value equal to n or beyond, then the present value random variable z will take a value of 0 because then the death benefit will not be paid by this particular type of contract. If you look at the symbol notation, we see an expression that is quite similar to the one we already discussed for the continuous time product. But now, of course, the only thing that is different is that the bar has disappeared, right? There is no bar because we're working here with a discrete time annual product. There is the duration n with the actuarial angle. There is the notation x, and there is the 1 on top of the x because this product is a term insurance product. So it refers to the fact that x, if x dies before the end of the contract, then the product will pay the death benefit. If you look at the valuation formula, we'll see that our k ranges from 0 to n minus 1. That's because the current future lifetime, the kx, can only take as the maximum value n minus 1 in this setting. We've got v to the power k plus 1 because we pay the €1 benefit at the end of the year of death. So if the kx is equal to k, then we're going to pay the death benefit at time point k plus 1. So we'll need to discount with a factor v to the power k plus 1. The probability that that's going to happen is the probability that kx is equal to k. So that is, as we explained last week, the survival probability kpx multiplied with the mortality rate qx plus k. So nothing or not much has changed compared to the formula that we derived last week. But do mind the upper bound in our summation formula. It's n minus 1. It cannot be n, right? Because then we would go beyond the duration of our, the policy duration, the duration of our contract. So if you're a little bit struggling with that, my recommendation is always to make a timeline and to carefully indicate on the timeline which scenarios are possible. And for your convenience, I've got such timelines at the end of the sheet of deck, the deck of sheets that I'm using today. So we will come back to those. The last one to be discussed in this section on term insurances is, of course, the employee case. So what now if we switch from the annual duration to a contract where we split the 1-year time period into m time periods of equal length? If m is equal to 12, then we split the 1-year duration into periods of 1 month. So what we're going to do here is we have the same principle as before. The death benefit is payable at the end of the 1/mth year of death, but only if that occurs now within a specific term, within a term of, say, n years, right? So what we get here is our present value random variable. Our present value random variable is the random variable z, which can be expressed as v to the power kxm plus 1/m. And this holds true if the kxm is less than or equal to n minus 1/m, right? So this kxm is capturing how many periods of length 1/m of a year my policyholder completely survived, right? So the maximum possible value that this kxm can take is n minus 1 over m, right? So if you look at the end of the duration of the contract, let's say that m is 12, so let's say you reason in months, then the largest possible value that your kxm can take is like the last month before the end of the contract. So be careful with that notation. Now, if you see then what is the actuarial notation for this expected present value, then things may become a little bit complicated over here. Because if you look at my notation here, you'll see that I let the k run from 0 to m times n minus 1. So that means that I let the k run in integers. K is 0, k is 1, k is 2, etc. But in my notation here for the valuation formula, I'm going to divide the k by m, right? So that in the end, I'm still working with steps, time grids of length 1 over m. So let me take a moment to clarify this on the iPad, because I know that it creates some confusion from time to time. So let's do that together. So my goal is to connect the expression for the valuation formula that we derived earlier on for the product that pays emptily, in emptily time grids, to connect that valuation formula with the one that you see here at the bottom. So let's take a moment to do this together. So last week, we derived the following expression for the whole life insurance product that works in periods of 1/n of a year. And we said that's v to the power 1 over m, 1 over m qx, plus v to the power 2 over m, 1 over m bar 1 over m qx, v to the power 3 over m, 2 over m, 1 over m qx, etc. Right? So here I was using mortality probabilities, deferred mortality probabilities of this type. And what I'm now going to say is, if you look at the notation that we just introduced for the term insurance that works in periods where we split the year into m equal time intervals, then we have the following summation formula. So that would be v to the power k plus 1 over m, and then you would have k over n px multiplied with 1 over m qx plus k over m. So you have to be a little bit careful here, because in this summation formula, this one, the k runs over integers. So the k runs like this, 0, 1, 2, etc. And the final value that my k can take is m multiplied with n minus 1. So for example, if k is equal to m times n minus 1, then if I look at, what can I say, v to the power k plus 1 divided by m, then that is equal to v to the power m multiplied with n divided by n, right? Yeah, so that is v to the power n, okay? Because that's what I want then. If I look at my, if I look at that happening in the very last period of length 1 over n, then the €1 benefit will be paid at time n. And so then I have to discount from time n to time 0, and I'll need the discount factor v to the power n, right? So that indeed works well. If the k takes this very last value in my sum, then my discount factor becomes v to the power n. If you would try one other, so let's say that if k if k is equal to, once again, m multiplied with n minus 1. Then if we look at k divided by m, for example, then what we get then is m multiplied with n divided by n. So that is equal to, minus 1. So that is equal to n minus 1 over m. And that's exactly what I would need if I'm looking, for example, at this survival probability. And so if I ask myself, yeah, if k is equal to m multiplied with n minus 1, and if I look at k divided by m, then I'm surviving for another n minus 1 over m years, right? And that's exactly what I want to have if I look at the timeline where my duration of 1 year would be split into intervals of length 1 over m. So you have to be a bit careful here, but that's how the notation works. So pay attention to the fact that is k running over integers, or is my k running over 1 over m like this. So in this notation, the k is running over the integers, and then I see that if I would write that in full, that I indeed get the setting that I want to have. So this is my valuation formula. If I look at a policyholder who is X year old, if I look at a contract with a duration of n years, and if I pay that contract, or if I make sure that that benefit will be paid at the end of the 1 over m year of that, then this will become my valuation formula. All right, so that concludes the different scenarios that I have for the term insurance product. What we're going to do now is we're going to jump from the term insurance contract to a new type of cover. And we're going to first look into the pure endowment setting. And once we understand what this pure endowment setting means, we're going to define a new type of insurance product, and that's going to be the endowment insurance. So let us look at what a pure endowment benefit, what it refers to. Well, a pure endowment benefit is paid conditional on the survival of the policyholder at the policy maturity date, right? So what is striking here is that we have a contract that's going to pay the benefit in case of survival, whereas up to now, we always discussed contracts which are going to pay the death benefit in case of death of the policyholder. So now we have something different. We're going to pay in case there is survival of my policyholder, right? So if I look at this construction, if I look at the present value random variable z with a benefit of €1 and a duration of n years, then that means that my z is going to be 0 if tx is below n, so if I don't survive until time n, and z is going to take the value v to the power n if the tx is n or beyond n. So whenever I survive until the end of the policy duration, this particular contract, this pure endowment, is going to pay me the €1 death benefit at time n. So discounting from time n to time 0 then goes with the discount factor v to the power n. Yeah, so this is a bit of a peculiar construction, but we'll need this to be combined with term insurance benefits to come up with the so-called endowment insurance product. So we're going to see later on how to combine these two. If you look at the notation, things now become complicated in the sense that we're going to play with the position of this superscript 1. So now we're going to put this superscript 1 on top of the n, because what we're interested in here is we're going to pay the benefit of €1 if the policyholder survives until time point n. So that's how I keep in mind, or how I try to remember this for myself. Where should I put the 1? Well, then you have to reflect, like, in which scenario are you going to pay the benefit? Are you going to pay the benefit if X dies before the end of the contract? Then you should put the 1 on top of the X. If you're going to pay the benefit if X survives until the end of the contract, then you should pay this 1 on top of the So Eric is asking, what's an example of this benefit in real life? And Sebastian says, yeah, like a pension. Well, it's not a pension in the sense that you get a monthly income, right, for the rest of your life, but you could see it like if you reach the retirement age, that then a certain capital will be paid. That indeed could be an example. But like my second bullet here says, we're often going to combine this thing with a term insurance benefit, such that you cover both scenarios that can take place: death of the policyholder within a certain period of time, or survival of the policyholder until a certain moment in time. Yeah? So very often this pure endowment is combined with a term insurance to be able to have a certain benefit being paid in case of death, but also in case of survival. And that's how you should see it. So be careful with the notation. We put the 1 on top of the N, and there is also this very weird and strange new symbol coming up, where the capital E is for endowment, pure endowment. The X is again referring to the age of my policyholder at policy at the start of the contract. And the N here at the left-hand side is now referring to the duration of the period that I'm considering. So I know this is quite overwhelming in terms of notation, but you really will get used to this by working more and more with this kind of product. So the capital E is referring to the pure endowment. So how do we value this product? Now, of course, only 2 scenarios are here for us to take into account. So either you die before reaching age x plus n, and that happens with a probability 1 minus npx, and then the random variable z will take the value 0 because we will not pay the benefit, or you survive until age n, or you survive until age x plus n, and that happens with a probability of survival npx, and in that case we're going to pay the €1 benefit at time n. So my discount factor will be my present value random variable will take then the value v to the power n, because I'm discounting the €1 from time n to time 0, right? So if you need to value this is pretty simple. To express the expected value of such a random variable z, it's a discrete random variable. It can only take 2 values, so the expected value will be the outcomes multiplied with the probabilities and that certain outcomes result. So in this case, that leads me to v to the power n multiplied with npx, right? So that is my actuarial present value for a pure endowment. Now, very often I get the question from students, what is here the difference between the continuous setting and the discrete time setting, right? So for example, students may also write the symbol with a bar or something, or they may struggle with like, is it a discrete product or is it a continuous product? Here, it doesn't matter, right? Because this product is only going to pay me €1 at time n in case of survival. So whether I value that in continuous time or in discrete time, it's going to be the same, because the probability to survive until time n, we know how to express that. That's the npx. Discounting from time n to time 0, that's the v to the power n. And that's the same whether we do that in discrete time or in continuous time. So with a pure endowment, there's no need to worry about the discrete versus the continuous time setting. Okay. So be careful about that, and that brings us right away to the very final product that I want to discuss in the first half of this class, and that's the endowment insurance. So the endowment insurance is going to combine a term insurance with a pure endowment, such that we have a benefit guaranteed whether we die within a certain period or whether we survive until a certain moment, right? So that is what we call the endowment insurance. For those who speak Dutch, in Dutch, you would refer to this product as een gemengde verzekering, because it's a mixed type insurance. It's both a term insurance in case of death and a benefit that you pay in case of survival. If we look at the present value random variable z, In case we have an insurance with a benefit of €1 and a duration of n years, then if the Tx is less than n, that means we're in the situation of the term insurance. So then the present value random variable will be expressed as e to the power of minus delta times Tx. If the Tx is equal to n or beyond, then we're in the situation of the pure endowment. So then the present value random variable is going to take the value v to the power n. So you can see this with a combined notation as v to the power, the minimum of Tx and n. As soon as Tx goes beyond n, then this minimum will just take the value n, and the z will take the value v to the power n. If the Tx stays below n, then this minimum will take the value of Tx, and you're working with v to the power Tx, okay? So what we need to worry about now, or what we need to figure out, is how to write down an integral expression for this particular type of product. And I'm going to start with an integral expression. So I'm going to start with an endowment insurance in continuous time. So that means if you die within the first n years of the policy, then the death benefit will be paid at the moment of death. Okay. What is the notation here? We've got the A bar, because we're working in continuous time. We've got the X for the age of the policyholder. We've got the N for the duration of the contract, and there is no 1, because we pay the death benefit for both scenarios, right? For death in period of n years, but also in case of survival until the end of the policy duration. Okay, so that's how this notation works. We're going to think about how to value this product by using an integral expression, but I suggest that I start with that right after the break. So if you have a question, now is a good time, and if you do not have a question, then you can enjoy the break, and we'll start again at 1 p.m. So what I introduced before the break is this continuous time endowment insurance product. So it's continuous time, and it is an endowment insurance. It's an endowment that means that it combines a term insurance with a pure endowment. And that's what we will see coming back in the valuation formulas that we put together. So if I would write down the expected present value of this thing. So if we write down the random variable z, then this random variable z will take the value v to the power tx. If tx is less than n, and we'll take the value v to the power n if the tx is larger than or equal to n. So that's what we start from. And of course, we're interested in figuring out the expected value of this random variable z. And as the definition of z already indicates, we're going to split up our valuation now, or our expected value calculation, in 2 integrals. So we're going to go from 0 to n, and then we're going to use e to the power minus delta times t. And we're going to multiply with the density function, the probability density function of tx evaluated in t. And then if we go beyond n, so from n to, say, plus infinity, we're going to work with e to the power minus delta times n. And again, what we're going to do is the density function evaluated in t, right? So that is what happens if I split up my expression. So we remember from what we derived earlier on, that this density function can be written as tpx, the survival probability, multiplied with mu x plus t, right? And the same applies over here. Now, of course, if we look at the first integral, then we recognize the valuation formula that we derived for a continuous time term insurance with a duration of n years. And if we look at the second valuation formula, well, then we see that e to the power minus delta times n can be put in front, and that we're left with the integral from n to plus infinity of my tpx multiplied with mu x plus t dt. So the question is, what is this integral, what is this expression going to be equal to, right? And what you get here is you take the integral of your probability density function from n to plus infinity. So what you're capturing here is the probability that Tx is larger than n. We're reasoning in continuous time, so whether I write strictly larger than n or larger than n equal to n, that doesn't matter. And of course, we've got a notation for that, that is the npx. So what is my valuation formula becoming? I've got a term insurance in continuous time with duration n. And on top of that, I've got e to the power minus delta times n multiplied with npx. And we also had a notation for that. So this one was my pure endowment. So with notation a, x, n with the 1 on top of the n. Yeah, so be very careful where you put this 1 and also where you put this duration angle, because during exams and during midterms, students are often a little bit sloppy with this notation, but sometimes it really means that you refer them to a different product. And so just be careful with your notation. So what do we have as expected for the endowment insurance? I've got a term insurance, in this case in continuous time, plus the value of the pure endowment. And for the pure endowment, like we mentioned, it doesn't matter whether you reason in discrete time or in continuous time, that's going to be the same expression. Questions on this? If this works well, then we're going to return to the sheets, and we're going to continue with our valuation formulas over here. So this is what we did. This is what I did on the iPad together with you. This is my expression for the expected present value of the endowment insurance in continuous time. If I would do this for the second moment, I'll get something similar, but instead of using the delta, I'm then going to use 2 times delta. If I would do the same for the annual product, then you'll get the same kind of reasoning. So the endowment insurance in discrete time with annual time periods, what does that mean? We're going to pay the death benefit at the end of the year of death, if that happens before time n. And if you survive until time n, you'll receive the benefit at time n, the benefit of €1. So again, the present value and the variable z, the definition of z is split into these 2 scenarios, which we can summarize by saying it's v to the power the minimum of kx plus 1 and n. So if you work out the valuation formulas, you'll recognize, in line with what we did together on the iPad, you'll recognize the valuation formula in discrete time for the term insurance with duration n plus v to the power n times npx, and that's again the valuation expression for the pure endowment with duration n, right? So that is in line with the continuous setting. It's just a matter of combining with the appropriate expression here for the term insurance part. You can also do the same if you work not with annual time periods, but if you split the 1 year period into m time periods of equal length. So here again, we're going to combine a term insurance with a pure endowment. The term insurance is active, or is going to pay the €1 benefit at the end of the 1 over mth year of death if kxm is less than or equal to m minus 1 over m. And if kxm is taking a value of n or beyond, so if you survive until hx plus n, then the present value random variable is going to take the deterministic value of v to the power n. So putting that together, we've got this expression. We're going to recycle the expression for the term insurance that works in periods of 1 over m of a year. And we're going to add on top of that the valuation formula for the pure endowment. Okay, so these were the different scenarios for the endowment insurance. What we keep in mind is that it combines a term insurance with a pure endowment. And the term insurance part, it can work in continuous time, it can work in annual, discrete time periods, or it can work in periods of 1/n of a year, right? And that determines then how we put these valuation formulas together. If this works for the endowment insurance, what we're then gonna do now is we're gonna continue with yet a different type of insurance benefit that we wanna be capable of finding the appropriate value for, and that is the so-called deferred insurance benefit. So what is deferred insurance? It's like what we discussed when we were talking about deferred mortality probabilities. So that means that we let our period not immediately start, but we're gonna offer the death benefit in this case, starting from the end of a certain deferred period on, right? So what we're gonna do here is we're gonna consider a benefit of €1 that is payable on the death of X, provided that X dies between ages X plus U and X plus U plus N. So this U in the notation, that's my period of deferment. That's the deferred period, right? So X should first reach age X plus U, and then the death benefit cover will kick in, will start to be valid. And in this case, if I consider a policy period of N years, I would have a term insurance product, but it would be a term insurance which does not immediately start providing a cover, but which only starts after this deferred period of U years, right? So that's the scenario I'm looking into in this setting. So if I write down the corresponding present value random variable, then the Z is going to be 0 if the TX is below U or the TX is above U plus N, right? Because we have this period of deferment, that's the U years, and we also have the duration of the term insurance contract here, which is N years. If TX takes a value between U and U plus N, then the present value random variable is going to be e to the power minus delta times TX. So the question is now, if you go to the calculation of the expected present value of this thing, how can you denote that? How can you write down this expression? So that's something we're going to do together. But first of all, what about the actuarial notation? Well, there has to be an extra symbol here, of course, because we have the deferred period, the U years. So that notation, that symbol is over here at the left side. So this U, similar to what we did in the mortality probability notation, this duration of deferment, the U, is on the left side with a bar. The capital A refers to the insurance product. The bar on top of the capital A refers to our continuous time setting. The X is the age of my policyholder. The N is the duration of the cover, the duration of the period during which the cover is guaranteed. And the fact that I've got the 1 on top of the X here refers to the fact that I'm looking at a term insurance contract. Yeah, so that's how this notation is being put together. Deferred insurance. So the U refers to, we're going to defer over the U years. The N refers to the duration of the cover. X is the age of the policyholder, and the bar refers to the continuous time setting. So if we value this product, we look once again at an integral expression of this type. But now, of course, we need to be careful with the boundaries of our integral, because our random variable Z will take a value of 0 if Tx is below U or if Tx is above U plus N. So the only duration for the integral we're interested in is between U and U plus N, right? Because we have this period, we have the X, which is time 0, and then we've got time U and time U plus N. So the cover only holds, in this case, if we're looking at this particular time period. So that's reflected in the boundaries of our integral. And if we're now going to manipulate this, this integral a little bit, what we then can do is we can rewrite it as such from 0 to n. And then we're going to do e to the power minus delta s plus u px multiplied with mu x plus s plus u. And we let the s run from 0 to n, right? So what I did here is I changed the t, and the t was running from u to u plus n. So I changed that into an s plus u, where the s is now running from 0 to n. That's the situation I put together over here. And the reason I'm doing that is because I can then rewrite my expression in an elegant way. So I could put e to the power minus delta times u in front. I can put the u px in front, and I can look at the integral from 0 to n, e to the power minus delta times s, sp x plus u, and then here I'm going to look at mu x plus s plus u ds, right? So if you now look at what I put in front, this is the, let's say, the actuarial discounting factor. If you need to discount over a time period of u years from time 0 on. Because what I take together here is the financial discount factor. That's the e to the power minus u. And the survival probability, that is the upx. So if I put it together, I got e to the power minus delta times u, upx. And then if you look at the expression over here, this is the expression for a term insurance with a duration of n years, but now a term insurance that is issued to an x plus u years old. So here I get a bar, and I get x plus u with a duration of n years, and I should put the 1 on top of the x plus u because I'm looking at a term insurance. Yeah? So here you also recognize a little bit what we did when we put the recursive relation together earlier on in this class. So you've got a certain actuarial discount factor, which is a combination of a financial discount factor and a survival probability. And what you then have is this term insurance, but now it's the term insurance issued to an x plus u years old. Okay. And this also comes in a certain sense back to Sebastian's question. So if you would wait until you have hx plus u to buy this product with a duration n, then it's going to be more expensive compared to when you would already buy it at age x, right? Because what we see here is we're going to multiply with this discount factor. Yeah, we're going to lower as such the value of this product. Okay, so that gives me the valuation product for the deferred life insurance. If you really like the actuarial notation, you could also write this as UEX, that's my pure endowment, multiplied with this A bar X plus U, and with a 1 on top of the X plus U. Yeah. You can also play a little bit more with these formulas. So what we do here is I'm going to split the integral from u to u plus n. I'm going to split it in the integral or write it as the integral from 0 to u plus n minus the integral from 0 to u. So what I recognize then is that my deferred insurance product, the EPV of that, can be written as a difference of 2 term insurance EPVs, one that I sell to an X-year-old with duration U plus N, and one that I sell to an X-year-old with just duration U. So this is another way of seeing how this term insurance with the period of deferment equal to U years, how that works. And you can see it as a difference of the EPV of two term insurances, one with a duration U plus N, and then the other one with the duration U. And you clearly see that here in the valuation formulas.